The transformer is a core deep learning model used in most modern language models today. Rather than processing words one at a time, it is designed to look at an entire sentence at once and focus on the most important relationships between words. To build a deeper understanding of transformers, this series is made up of 4 videos. In this video, we'll explore the structure of the transformer and how words are converted into a form that the model can understand. First, let's look at the limitations of traditional RNN-based sequence models. Because these models process inputs sequentially, parallel computation is difficult, and training on long sentences takes a significant amount of time. LSTMs addressed some of these issues, but long sequences still suffered from the long-term dependency problem. The figure below shows the sequence-to-sequence architecture before the introduction of attention. In this structure, the entire input sequence is compressed into a single context vector. Whether the sentence is short or long, all information has to be packed into one fixed size vector, which means that as sentences get longer, important information is more likely to be lost, and semantic degradation becomes severe. The transformer was introduced to overcome these limitations. Now, let's briefly look at how deep learning-based language models have evolved over time. RNNs, introduced in the 1990s, made it possible to process sequential data, but they suffered from the vanishing gradient problem when dealing with long sentences. LSTMs improved on this by alleviating long-term dependency issues, yet they were still difficult to parallelize due to their sequential nature. Later, sequence-to-sequence models with attention significantly improved translation performance by allowing the model to refer to all words in the input sentence, but they still retained an RNN-based structure. In 2017, the transformer was proposed, enabling parallel computation through self-attention and becoming the foundation of modern natural language processing. Building on this, GPT leveraged large-scale pre-training and ushered in the era of general-purpose large language models. All right, let's talk about the transformer. In 2017, researchers at Google introduced a new model called the transformer in their paper, "Attention is All You Need." This model completely removed the traditional RNN structure and was built solely on self-attention. It enabled parallel processing while delivering excellent performance, and it went on to become the standard architecture for modern NLP models. The source of the paper is listed below, so if you have time, I recommend checking out the original yourself. The figure you see here shows the overall architecture of the transformer, as presented in the Attention is All You Need paper. The input sentence is first converted into vectors through an embedding layer, and positional encoding is then added before the data is passed to the encoder. The encoder is made up of multiple identical layers, and each layer consists of multi-head self-attention and a feed-forward network, with residual connections and layer normalization applied to every sublayer. In the decoder, masked multi-head self-attention is applied first, followed by encoder-decoder attention, and then a feed-forward network. Just like the encoder, the decoder also includes residual connections and layer normalization in all of its sublayers. In the previous slide, we looked at the overall structure of the transformer. Now, let's zoom in on the encoder and decoder in more detail. In the transformer, both the encoder and the decoder are built by stacking multiple layers that all share the same structure. In other words, a single encoder layer and a single decoder layer are repeated multiple times. In the original paper, Both the encoder and the decoder consist of 6 layers, and these layers are connected sequentially. The output of the final encoder layer is then passed to every decoder layer, where it is commonly referenced in the encoder-decoder attention mechanism. Now let's briefly look at how embeddings work in the transformer. The input sentence is first tokenized into individual tokens. For example, I like baseball better is split into I, like, baseball, and better. Each token in the predefined vocabulary is assigned a unique integer ID, and each token in the input uses this ID to look up its corresponding vector in the embedding table. For example, if I has ID 12 and like has ID 508, the model retrieves the matching vectors from the embedding matrix. You can think of this like using a dictionary. When you open the page for the word apple, you find its definition. In the same way, the token ID acts like a page number, and the row vector on that page represents the meaning of the word. In the original transformer, each token is represented as a 512-dimensional vector. These embeddings are used as inputs to the encoder and decoder. However, embeddings alone do not contain any information about word position. That's why next we'll look at why positional encoding is necessary. Now let's look at positional encoding. In traditional RNN-based models, inputs are processed sequentially, so information about word order is naturally captured by the model's structure. In contrast, the transformer processes the entire sentence in parallel, which means that the input embeddings themselves do not contain any information about word order. To address this, the transformer explicitly provides positional information for each word using positional encoding. The representative method proposed in the paper is sinusoidal positional encoding, which uses sine and cosine functions, as shown in the equation below. These values are bounded between -1 and 1, and the same position always has the same positional encoding. The resulting positional encoding is added to each word's input embedding, allowing both semantic information and positional information to be represented together. Importantly, the positional encoding is designed to be small relative to the embedding values, so that it does not excessively distort the meaning of the word embeddings. Now, let's look at a simple example of how positional encoding is actually applied. The example sentence is, I like baseball better. After tokenization, it is split into 4 tokens. I, like, baseball, and better. In the transformer paper, the positional encoding for each token is defined as a 512-dimensional vector. To make the calculation easier to understand, we'll focus only on the first 2 dimensions, dimension 0 and dimension 1. Each token is assigned a position based on its order in the sentence. Positions 0, 1, 2, and 3. In the table below, the position values are directly substituted into the sinusoidal positional encoding formula, with the sine function applied to dimension 0 and the cosine function applied to dimension 1. For example, the token I at position 0 has a 512-dimensional positional encoding vector, whose first 2 values start as 0, 1. The token like at position 1 has a positional encoding vector, whose first 2 values start at approximately 0.84, 0.54. In this way, each token receives a different positional encoding based on its position, enabling the transformer to recognize and use word order information. Now, let's see how positional encoding is combined with the input embedding. In the transformer, the final input vector for each token is formed by adding the input embedding and the positional encoding. In the table we looked at earlier, an example input embedding vector is assigned to each token along with the positional encoding vector for its position, and these two vectors are added element by element to produce the final vector that is fed into the encoder. In this process, the input embedding captures the semantic meaning of the word, while the positional encoding provides information about the word's position. By adding them together, both types of information are naturally combined into a single vector. As a result, the encoder can take into account not only the meaning of each token, but also its order within the sentence.